Okay, so this is part 2 of the video sequence on impulse and momentum conservation. In the last video we defined impulse and gave some examples. In this video we're going to show how it leads to momentum conservation under the right circumstances. So this is part 2. It's a little bit faster than the part 1. I think for an example on this, let's think about our carts that explode apart. We did a lab with this where you've got 2 carts. Okay. There's a spring, right, that's going to push them apart. And of course they fly off in different directions. I'm going to call this cart 1, I'm going to call this one cart 2. And so the thing to think about first of all is the fact that these objects are interacting, okay? And we're going to think about these interacting objects inside of a system. Okay. This is an isolated system. In the previous video we talked about a force acting from the outside, and that was going to cause a change in momentum. In this example we're going to talk about the system being isolated, and what that means is that the 2 forces that act here are inside of our system. So what that means is that when the spring pops, one is going to push on 2 with a force that goes to the right. That's the force of 1 on 2. That's the action force. But by Newton's third law, there's a reaction, which is the force of 2 on 1. And those forces are both inside the system. And that's important. Okay? So we're going to write that down. We're going to say that the force of 1 on 2 is going to be equal and opposite to the force of 2 on 1. So I'm going to put a negative sign there because they go in opposite directions. And that's all because of action and reaction. Those forces are action-reaction pairs, or an action-reaction pair. Okay, so hopefully you can see that. And they're both inside of the system. So they're both within the system. Okay, now in the next several lines, I'm going to basically just start with this, and I'm going to add a couple things in, and I'm going to basically end up showing that the momentum of this system has to be conserved. That means that if you look at the carts together, that their changes in momentum individually will have to cancel each other out, and so that no momentum is given to the system or taken away, but you end up with the same amount overall. So the first step that we'll do is we're going to use common sense and logic. And I'm going to simply write, I'm going to just write F12 from now on. But I'm going to write this. I'm going to write logic here. And here's what I mean by that. In algebra, you're told that you can multiply 2 sides of an equation by the same thing, and you don't change the equation. That's exactly what's happening here. And I'm saying that I'm going to multiply both sides by delta t. The delta t is the time that the carts interact with each other. It's fast. It's a short time because they only push for a split second. However, the time that 1 spends pushing on 2 has to be equal to the time that 2 spends pushing on 1. It would be impossible to be otherwise. You know, how could that work? So these 2 t's, the time intervals are exactly the same. All right. You can't have one cart pushing on the other cart longer than the vice versa. Now, the reason that I introduced that here is because I hope you recognize that that's actually impulse. And we know from our relationship that impulse changes momentum. So I'm going to now replace all of this stuff on the left with the change in momentum for cart 2, because there's going to be a change in the momentum for cart 2. Because of the force that acts on it. So I'm replacing this with this. And over here, I'm going to carry the negative sign down, and this is the force of 2 on 1. Therefore, this must be the change in momentum for cart 1. So now we're using the impulse-momentum relation. Okay. And now we're cooking, you know, because you can see that if I bring these 2 things on the same side, I've got something that looks hopefully familiar to you. that should be looking like what we wrote for energy conservation. Remember, like not too long ago, we talked about delta K plus delta U equals 0, and that means that mechanical energy was conserved. Well, now you've got a change in momentum for one object plus a change in momentum for the other is equal to 0. That's actually saying that momentum is conserved. So momentum is conserved in this isolated system. Okay? And it's important to remember that the system is isolated because there's no net external force, meaning nothing is coming from the outside. So these carts should be completely isolated. So that's basically the idea here. So there should be no overall change in momentum, and so momentum should be conserved. I think that it's probably something we've done already, but you know that you can also rearrange this, right, by saying that P1 final minus P1 initial plus P2 final minus P2 initial. That can lead you to kind of a useful version of this. P1 initial plus P2 initial equals P1 final plus P2 final. And so a lot of times in problem solving, we'll say that the momentum before something happens has to add up to the same value of the momentum after it happens. So this is probably a good practical thing to use. Okay. Now, if you have a problem where the system is not isolated, so let's say that you've got some object here, right, and you come back to a situation where there's some type of an external force that acts on it, then the way you can deal with it is, again, you can just say delta P, and instead of saying is equal to 0, now you're going to say it's equal to the impulse from that force, right? In other words, the F external times T. And that's a lot like what we said with energy, where if there's a change in energy in the system, if the system is not isolated, there's work that's being done. So this is a lot like delta E is equal to the work external. Okay, so this is for non-isolated systems. I'll give you an example of that. You can think about this. So there are two common examples of non-isolated systems. One of them might be, what if you put your carts on a ramp and had them explode? Okay, because then you do have an outside force coming from gravitational parallel force that acts on those. So that's an example of a non-isolated system. Another example would be, what if you took the wheels off the carts and you had them basically slide on some kind of a rough surface with friction? Well, then there's going to be an outside force acting on each one of those things, and you would have to account for that by finding the impulse over here. Those problems get a little more challenging, but that's how you would deal with them. All right, so we're going to leave it, and then you guys can look at some practice problems.